This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Welcome to the Birch Aquarium at Scripps and the Jeffrey B. Graham Perspectives on Ocean Science Speaker Series. My name is Cheryl Peach, and I'm a project scientist here at the Birch Aquarium, Scripps Institution of Oceanography, UC San Diego. It's my great pleasure this evening to introduce our speaker, Dr. Eric Sperling. Eric is with us here today as a postdoctoral researcher at Scripps Institution of Oceanography. But he began his career as a scientist and a geologist at Stanford University, where he received his bachelor's degree. He subsequently attended Yale University, where he received a doctorate in geology with a specialization and emphasis in paleontology. And then, wanting to be sure that he rounded out his academic training, his professional training at the finest institutions, he did a postdoc at Harvard, and then his second and current postdoc here at Scripps Institution of Oceanography, UC San Diego. It's also my great pleasure to announce that Eric will be taking up his first formal professorship position at Stanford University this fall. So we're really quite pleased for Eric and his wonderful career thus far. As I said, his expertise is in paleontology, and Eric uses Earth history to incorporate data from modern oceans and modern oxygen minimum zones to increase our understanding of how changes in oxygen levels can influence evolution, both in the past and also possibly in the future. So please join me in a warm welcome for Dr. Eric Sperling and his talk titled Breathless Through Time, How Oxygen Can Alter Evolution and Adaptation of Life in the Ocean. Eric, thank you very much for being here.
All right, well, thank you all for being here. It's really great to have an opportunity to talk, and thanks for the organizers for inviting me. You've all been staring at this fairly gruesome image for some time now as the talk got started, and I chose it. It's a fish kill from Redondo Beach Harbor that was probably caused or influenced by low oxygen to illustrate the simple fact that animals need oxygen. It's our most fundamental requirement, and without it, we'll die. Now, I've been interested academically in the interaction between oxygen and evolution for quite some time, but apparently I've been interested in oxygen for much longer. So my parents just recounted this story to me last week. This is me in the middle, and we're on a hike. I grew up near Seattle, and we're on a hike into the mountains outside Seattle. And I was really worried. Somehow I had heard that the air up at higher elevations had less oxygen in it. So I took a water bottle like this, and I filled it full of air in the trailhead, which apparently just meant I closed it. And then I threw it in my backpack, so that if we got up too high and there wasn't enough oxygen, I have an emergency supply of air from lower down. Now, I didn't need oxygen up at 4,000 feet elevation, but what this does illustrate is that oxygen levels vary throughout the Earth, and they influence where and what kind of species can live in certain places. So in today's talk, I'll be talking about how oxygen levels in the atmosphere and ocean, the Earth system, have changed in the geological past, and how these changes have influenced the course of evolution of life on Earth. And finally, I'll be concluding the talk with talking about the implications of these ancient oxygen changes for the health of our future oceans undergoing global change. So this slide sums up what geologists think we know about the history of atmospheric oxygen on Earth. And today we're going to be talking about a lot of ancient times and ancient oceans and parts of the geological timescale that most people probably won't be familiar with. So I'm going to keep returning to this image and to the geological timescale at several points throughout the talk in order to reorient you. Basically, what this shows is this is a geological timescale from present back to about 4.5 billion years ago. And this axis is the atmospheric oxygen and what we call percentage of PAL, which is just present atmospheric levels. So this 100 here represents the present levels. So there are basically three main stages to the evolution of the Earth's atmosphere component. In the first stage, the early part of Earth's history, the atmospheres and oceans contained basically no oxygen. They're what we call anoxic. Oxygen levels then rose orders of magnitude, but still to relatively low levels compared to the modern at about 2.4 billion years ago. This is what we call the Great Oxidation Event. During this middle part of Earth's history, atmospheric oxygen is thought to have remained relatively low and steady, about 1 to 10% of present levels. And then oxygen rose to essentially modern levels about 600 million years ago and kind of fluctuated around that level ever since. So let's zoom in here on this geological timescale, again from 0 to 4.6 billion years ago, which coincidentally is the age of Earth's formation. The oldest rocks we have present on Earth are up in northwestern Canada at about 4 billion years ago. Now, the things we think about as old in the geological record, typically, things like the dinosaurs, they actually occur right here. So geological time is incredibly long. And geologists have a metaphor that we try to use to explain the stretch of geological time. And what we do is we say we're going to compress this entire 4.6 billion years of history into one calendar year. So in this calendar year, these oldest rocks show up sometime around late February. The dinosaurs don't show up till the very end of the year. They show up around December 12th, and they only exist for about 2 weeks before going extinct right after Christmas, December 26th. The earliest humans don't appear until New Year's Eve, specifically 11:48 p.m. And Stonehenge was built about 30 seconds before the ball dropped. So during today's talk, we're going to be talking about 3 different stories, some of the best stories in Earth history about oxygen and evolution during these fairly long stretches of geological time that most people don't generally think about. The first story will be the Great Oxidation Event and the origin of atmospheric oxygen about 2.4 billion years ago. Then we'll talk about the Cambrian Radiation and the origin of animals in the fossil record at about 540 million years ago. And finally, the Permian-Triassic mass extinction, where almost all life in the oceans went extinct about 250 million years ago. And finally, we'll be talking about the future of our oceans. So we'll start first with the Great Oxidation Event about 2.4 billion years ago. Now, we know from a number of lines of geological evidence that the oceans at this time period contain no oxygen. One of the most striking ways we know this are these banded iron formations, such as this one, the Brockman Iron Formation in Western Australia. And what these are essentially reduced iron that is just rained out and precipitated from the water column. And if there had been any oxygen present, this reduced iron would have just precipitated out and not been present. Now, while these are interesting from a geological perspective, they're more important to human history in the growth of our industrialized society. So this is a photo I took the Tom Price mine in Western Australia, where they're mining the Brockman Iron Formation. And it's this iron that's being used, shipped off to China to build the steel for much of their modern expansion. Similarly, it's Precambrian iron formations, a little younger in this case, from the upper mid-continent of the US, which has provided all the iron for the steel for the Detroit iron makers. So these old ancient iron formations are basically where our iron for steel comes from. But now it's not just the oceans that were anoxic at this time, it's also the atmosphere. And we know this again through many sources of geological evidence, but one of the most important are what we call redox-sensitive detrital grains, such as pyrite or fool's gold. And what we see is that if we look at this chemical equation, if there's any oxygen present, pyrite is going to oxidize and disappear. So basically, in the modern ocean, we never see, or the modern sediments, we never see pyrite entering the rock record as detrital grains. In contrast, in the Precambrian, such as this rock sample from South Africa, we find detrital pyrite present with all these rounded rocks, little cobbles, which indicates these sediments have transported a long way. Now, if we look at the distribution of these through Earth history, what we see is that these detrital pyrites only appear before 2.4 billion years ago, and after that, they're present. When we go past 2.4 billion years ago, instead we see what are called red beds. This is just oxidized iron in soils. So if you've ever driven around the desert Southwest and see those spectacular red rock formations, that's just the oxidized iron in soils that's occurring under an oxidized atmosphere. So 2.4 billion years ago is the time when we know that oxygen first started becoming present in the atmospheres and oceans. But now the question is, if oxygen is present in the atmosphere and it's kind of spread widely throughout the world, there are some slight differences with respect to elevation like I talked about, but it's mainly homogeneous. How do we get low oxygen zones in the ocean? Well, in the oceans, most oxygen, or all oxygen, is created through photosynthesis. And in this process, phytoplankton, or algae, takes CO2, light, and nutrients like nitrate and phosphate, and uses this to create organic matter and oxygen. The surface of the oceans are in what we call equilibrium with the atmosphere. So this oxygen goes back out and then mixes back in through the action of waves and wind. However, this, what we call the mixed layer, the place where the waves and wind can mix the oxygen back in, only occurs down to several tens or hundreds of meters. And below this, that oxygenated water can't penetrate and mix in. So what happens is that these phytoplankton, after they die, they sink down. And once they've sunk down below the mixed layer, they start to decompose. And they do this through the process of respiration. Respiration is just the opposite of photosynthesis. So when you take a breath in, your body's going to take that oxygen and use it to burn or respire organic matter to produce energy. And also you're then going to exhale out this CO2. So basically this decomposition of the organic matter is going to occur at the expense of oxygen. So if we look at a graph of oxygen levels in the ocean with respect to depth, we see they start out high and constant through the mixed layer. And then once we get down to the mixed layer, and you start seeing organic matter decomposing without any new oxygen coming down to replenish it, the oxygen levels start to drop. So if we just look at this figure then, there are a number of different levers that we can play with in order to get low oxygen in the oceans. One of the easiest is simply to just have lower levels of atmospheric oxygen that you're mixing in. This is particularly relevant for that middle part of Earth history. A second way is to allow less oxygen to mix in during that process. So one example of this is temperature. In warmer oceans, less oxygen mixes into the water. It's less soluble. Another way is to reduce the physical mixing process itself. If we can create kind of density layers that make it physically harder to mix, we can make it harder for that oxygen to mix in and replenish the levels that are lost to respiration. And the final way, and probably one of the most important, is if we can simply get more nutrients into the upper water column, because most of these phytoplankton are limited by the presence of these nutrients like nitrate and phosphate. And if we can do that, we can get more phytoplankton growth. There will be more organic matter sinking down and more decomposition. So we look now at where we see these processes occurring in the modern ocean. That nutrient one occurs oftentimes on upwelling margins, such as the California margin here. What happens in upwelling margins is that you get a wind along the coast, or wind stress, and this interacts with the Coriolis effect to push that surface water off the shore. What happens then is nutrient-rich deep water then rises back up to the surface to take the place of that water that's moved offshore. And these nutrients fuel that extra primary productivity. And so if we look at a map of oxygen against depth, this is at 250 meters depth, we see that these low oxygen levels, these kind of purples and blues, primarily occur along the western upwelling margins of continents. For instance, in South America, North America, the western margin of Africa, and there's also monsoon-driven upwelling in the Indian Ocean. While that's a natural process, this also occurs in the modern ocean due to human influences. If you just dump a lot of nutrients in, you're going to get increased phytoplankton growth, what we call eutrophication, and a decrease in oxygen. And this is particularly happening off the coast of Louisiana and Texas, where the Mississippi River is bringing large loads of nutrients down to the Gulf of Mexico and fueling extra primary productivity. And you can see along the coast here of Louisiana and Texas, the oxygen levels are dropping almost to zero. And this is a major problem worldwide, and it's happening in coastal and estuarine systems all around the world. Basically, anywhere there's a lot of people and a lot of agriculture and a lot of excess nutrients coming into the system. The final way we can get low oxygen settings is if you have some sort of strengthening of these density differences, so you get less mixing of the system. And this often happens in kind of restricted water masses, such as estuaries or places like the Black Sea, where it's harder to mix in. So anytime you have a density difference due to temperature differences or salinity differences, it can be harder to physically mix the system and bring that new oxygen in. So moving back to the geological record now, how do we actually recognize low oxygen in the geological record? This is kind of what is the primary data for me as a geologist. Well, the easiest way to recognize it is simply looking at the color of a rock. If you see a really black rock like this dark shale, chances are it has a ton of organic matter in it, and that organic matter has been fueling excessive decomposition and has resulted in low oxygen. And it's no coincidence that these kind of black shales are our basic source rocks for modern petroleum systems. A second way we can infer ancient conditions is by the presence of specific fossil groups. So paleontologists know that there are some fossil groups, like ammonites and graptolites, that only live in the upper layers of the water column. So if you see a rock like this one, which only has fossils that are living in the upper water column, and nothing living on the seafloor, the benthos, you can infer that there was something that made those bottom waters inhospitable, and oxygen's a good call. If there are benthic faunas, things living on the seafloor, they can be further used to calibrate how much oxygen was actually present, because geologists have known for a long time that the level of oxygen can correlate with how diverse a fauna is present. So as you go down in oxygen, you lose these big forms, you lose diversity, and ultimately you're often left with just a single species that can tolerate those conditions, what we call a monospecific assemblage. So this is an example from the Wheeler Shale in Utah, where it's just one trilobite species that can tolerate these conditions. And this is an example from the Triassic of Spitsbergen, where it's basically just one bivalve species, Chloria, that can tolerate the conditions. It's not just the body fossils, though, that can be used to tell us about ancient oxygen levels. Animals also burrow through the sediments and leave traces of their activity in the geological past. These are what we call trace fossils, and some of them are quite spectacular, such as these here. And so these organisms are moving around and burrowing through the sediment, we can infer that there's plenty of oxygen. In contrast, rocks deposited underneath low to absent oxygen conditions have this perfectly flat, laminated appearance with no disturbance to the laminations. And finally, there are geochemical methods to recognize anoxia or hypoxia. And I don't want you to freak out about the geochemistry here. I'm basically just trying to put across the point that geochemists can tell how much oxygen was in a rock based on its chemical constituents. So this is just some work done by Tom Algeo and colleagues. And this is a nice black shale that's overlain by this gray shale that has all these trace fossils in it. That's what all these little squiggly lines are supposed to represent. And you can see that the black shale is enriched in iron, and all of these what we call redox-sensitive trace elements. These are things like molybdenum and uranium and vanadium, things that are enriched under anoxic water columns. And again, the point here is not to focus on the details, just to note that we do have geochemical fingerprints of low oxygen conditions also. So with this background on oxygen in the modern ocean and how we recognize it in the ancient oceans, we can now move to our second story, the Cambrian Radiation. And this is the time period where the first big complex fossils show up in the fossil record. And my colleagues that work on the unicellular fossil record, the fossil record of single-celled organisms, will be a little insulted by this comment. But there's basically nothing going on in the fossil record for billions of years of evolution. And then suddenly, at 540 million years, we see animals for the first time, first large things in the fossil record. And the question is why? And this is really one of the most perplexing things in evolutionary biology. And in fact, it really stumped Darwin, and he suggested it was one of the prime challenges to his theory of evolution. Because the geologists of this time knew that all the fossils, all the echinoderms, the trilobites, the brachiopods, all showed up at this one specific point in the rock record, and there was nothing beneath it. And Darwin, who kind of believed in this slow and steady unfolding of evolution, he thought this was a big problem. So he writes in The Origin of Species, "There is another and allied difficulty, which is much graver. I allude to the manner in which number of species of the same group suddenly appear in the lowest known fossiliferous rocks." Now, we've learned a tremendous amount about early animal evolution in the time since Darwin. But the severity of the explosion, the temporal time in which all these groups show up in the fossil record, hasn't changed. And goodness knows that's not for lack of trying. So just to illustrate this, I'm going to talk a little bit about my fieldwork. I'm fortunate enough to work up here in northwestern Canada in kind of this arcuate belt of rocks from the Alaska-Yukon border down to British Columbia. And this is one of the most wild and remote places still left in North America. And it's seen very few geologists that have actually gone out and looked at these rocks. So it's a great place to find new fossils. So for instance, last summer, we flew into Whitehorse, and we drove down to Watson Lake, which is a town of about 1,000 people. And it's mainly famous for its extensive signpost forest. We then took a dirt road up here for about 6 hours and got to a little mining town called Tungsten, which has this little dirt airstrip. And at this airstrip, there's a helicopter that flew us out about an hour into the Mackenzie Mountains, dropped us off, and flew away. And left us on this truly spectacular exposures of what's known to geologists as the Windermere Supergroup, which is this set of rocks that was deposited about in the 200 million years before the Cambrian explosion. It's a perfect place to find fossils if there were any. Now, most of our work when we're out there is relatively basic. It's mapping, describing the sediments, collecting samples that we bring back for geochemistry, because it's hard to get money just purely for exploratory paleontology out there. But you better believe it that we keep our eyes absolutely peeled when we're out there for any Precambrian animal fossils. Because if we did find any, it'd be huge. We'd be famous. Or famous to like a certain subset of paleontologists, but you know. But year after year, we go out to places like this where there haven't been geologists and we don't find any new fossils. And there are other people going to every other unexplored bed worldwide and not finding fossils. This is just another picture of my colleague Justin Strauss that I do a lot of field work up there. And he's kind of forlornly looking at the middle member of the Backbone Ranges and hoping that there's going to be a Nature paper worth of new Precambrian animal fossils in there. But we've yet to find that. In contrast, you go just 40 million years earlier in the geological record into the Cambrian, and there are fossils everywhere. You go to any Cambrian deposit, and you're probably going to find shelly fossils like trilobites and brachiopods, clams, and so forth. But what's truly spectacular, the best record of the Cambrian explosion, are in these places called Burgess Shale type deposits. And these are interesting because they not only preserve shelly fossils, but they preserve fossils with only soft parts as well. And the Burgess Shale itself is located here in British Columbia, kind of on the British Columbia-Alberta border. And if you're ever up here in kind of the Calgary, Banff, Lake Louise area, I would strongly suggest making a day trip to the Burgess Shale. Parks Canada and the Burgess Shale Foundation do a fantastic job leading tours there. And I think it's one of the absolute coolest things you can do if you're interested in Earth history and science. This is our guide, Tom, a couple of years ago. And it's not just the science that's interesting here, because the Burgess Shale is in one of the most beautiful and spectacular sites one could ever hope to find fossils in the world. So you kind of start this hike here down in the valley and hike up here into the Alpine. You get to take lunch at these kind of spectacular outcrops overlooking some amazing mountains and glaciers. You get up to the Burgess Shale itself, and you're looking down on these amazing glacial lakes. This is Emerald Lake, and over again to some amazing glaciers and mountains. And the great thing is there's fossils everywhere. I should point out that this is kind of a hard hike. This is about 14 miles round trip with a decent amount of elevation gain. But basically anyone can do it if you want it hard enough. This is my mom here in the Burgess Shale Quarry, and she's in her late 60s, so if she can do it, I'm sure you can do it. She's holding here what's a little brachiopod, which is one of my favorite groups. They have some spectacular examples in the Burgess Shale. Brachiopods are a group of organisms which are related to and look like clams. They have the same sort of bivalve shell, but they actually evolve their shell independently. This is a fantastic specimen of Micrometra, showing these really nice cedal spines. There's also more familiar organisms in the Burgess Shale, for instance, trilobites. This is a little crustacean-like organism called Waptia. polychaete worms. There's also some truly spectacular organisms that people still don't really understand, like this Opabinia, which has 5 eyes on its head and kind of this long grasping claw that can reach out and grab organisms with. So this is an artist's reconstruction of the seafloor in the Burgess Shale. And what's truly interesting about the Cambrian radiation is not just the appearance of organisms in the fossil record, but that basically every major animal phyla, or every major animal body plan that we see in the modern ocean is present in the Burgess Shale. So here's what's called a preapulid. Here's an arthropod, that's that little crustacean Waptia. Here's a polychaete getting pulled out of its tube by this Opabinia with the 5 eyes on its head. This is an early chordate swimming around. There's sponges and brachiopods hanging off them. There's basically every modern group, but as I hopefully illustrated with our example of our work in Northwest Canada, if you go just 40 or 50 million years earlier, there's nothing there. This graph just hopefully illustrates that a little more quantitatively. What this is just the cumulative appearance of every animal phyla in the fossil record in blue and animal class in yellow. And you can think of these as just kind of bins that taxonomists put animals in order to count up diversity. And this is a geological timescale from 800 million years ago up to 450 million years ago. With the Cambrian boundary, the stuff below that is known as the Precambrian, Cambrian boundary right there. What's really interesting about this is that what's shown here, these arrows here, point to the number of total living phyla and total living classes. So what this illustrates is basically all the modern body plan diversity showed up in that first 20 or 30 million years of the Cambrian. And the big question then is, of course, is why did it happen? And geologists have, for decades, related this causally to this second oxygen increase in Earth's oceans, which happened about the same time. And so what people have suggested is that the rocks before, or the oceans before the Precambrian, simply didn't have enough oxygen to enable large complex organisms to live in there. And indeed, if we look at the rocks, we can see that. So this is a picture of another of my field areas up in northwestern Canada. It's the Ogilvy Mountains about 800 million years ago. And you can see that these rocks are jet black, and I've investigated the geochemistry of these pretty extensively, and they show a clear low oxygen signal. But another group of paleontologists have questioned this, and they've said, well, I can understand why an increase in oxygen would cause an increase in body size, or perhaps a few more species, but why would things evolve into these vastly different body plans, as different from each other as a polychaete and a mollusk, if you just increase the oxygen levels? So this famous painting, or this amazing painting, is Bruegel's Big Fish Eat Little Fish. And it's been used by Nick Butterfield in Cambridge in his talks, and I've subsequently stolen it from him. Now, Nick's argument is relatively straightforward. It's just that big fish eat little fish, and kind of in this ensuing struggle to either eat or be eaten, animals develop these new body plans and morphological innovations to aid in this struggle. And this makes a lot of sense. What I found interesting in thinking about this is that the carnivory, the act of an animal eating another animal, what Nick's hypothesis is relying on, actually has a large cost of oxygen. So there's the obvious one, which is just simply the energetic cost of capturing and subduing a prey. But there's a second cost, which is a little less obvious. It's what we think of as a food coma. But in physiological terms, it's measured by the specific dynamic action. It's the metabolic response that accompanies meal digestion. And so what we hypothesized was that if you're living in a low oxygen ocean, it's going to be much easier to be something like a deposit feeder or a filter feeder, something that can kind of slowly reach out and bring small particles of food to yourself, than a carnivore that has to chase down and capture its prey and then is sticking a huge bunch of food down its neck and basically has to experience Thanksgiving dinner every time it feeds. Just to illustrate this, I have this little movie. And this movie is of a Nemerdian, which is one of the groups we think may have been the first predators present in the Cambrian. And what it's going to do here is to just shoot out its proboscis and capture this poor little polychaete worm. And you can see that this is not an easy struggle. These organisms are fighting for their lives, and this is an energetic, oxygen-intensive battle. What the marine is going to do now is it's going to start shoving this polychaete whole down its mouth. So this is basically the marine equivalent of a snake swallowing an entire small mammal. And now it's going to start crawling away. And you can actually see little bits of the polychaete sticking out within it. So in order to test this hypothesized relationship between oxygen and feeding strategies, particularly the ability to be a carnivore, we actually turned to that other group of organisms, the polychaetes. And we did this for several reasons. First, polychaetes are the most abundant organisms in deep sea low oxygen environments. Second, their feeding biology is relatively well known. And finally, they have a diversity of feeding modes within this group. So for instance, there are deposit feeders like this terebellids, carnivores, often with these well-developed jaws like this polynoid, filter feeders like the serpulids, and even the famous chemosynthetic tuberums. So to do this study, I took published data and coded the likely feeding strategy for about 1,100 different polychaete species occurrences, which was about as much fun as it sounded, from 68 stations or areas in the world's ocean, which are shown here. The main low oxygen areas of the ocean are shown here in black. This is the results of the study. I don't want you to get too caught up on the details. What this is basically showing is the percentage of carnivorous individuals in an area of the ocean against 4 different oxygen levels. And these red bars represent the median for each of those different oxygen levels. What you see is that there's a clear increase in the percentage of carnivorous individuals at a station as oxygen levels go up. We also looked at the number of carnivorous taxa or carnivorous species at a station, and again, we see an increase in carnivorous species present as you go up in oxygen levels. So at least for polychaetes in the modern ocean, there's a strong relationship between oxygen level and the ability to be a carnivore. And I should note that just on this lowest oxygen station, amazingly 14 of the 28 stations, nearly 50%, have 0 predators whatsoever. So in kind of summing up the Cambrian radiation, this origin of the first large organisms in the fossil record, and basically all of our major animal body plan diversity, I think that both these two camps of people are right. I think that it probably was these predator-prey arms races and these animals eating other animals and kind of the fight for survival that caused this burst of morphological evolution. But I think the geochemists and some of the other paleontologists are also right that the oceans before then were probably oxygen limited for the presence of predators. So we'll now come to our third point, or third story on the geological timeline, which is the Permian-Triassic extinction. And what this illustrates is the last story illustrated that oxygen can giveth, and this basically shows that oxygen can taketh away. Oxygen is one of the strongest controlling factors on diversity in the modern ocean. What I'm showing here is just some plots illustrating how oxygen affects diversity in the modern ocean. So what we did was we took all those places where we had data for the polychaetes in that last study. We took all the organisms there, not just the polychaetes, and we calculated a diversity index, what's called the Shannon H' index. And I don't want you to get too hung up on this. Basically, you can think of low values of this as representing communities that are not very diverse, perhaps only a few species and dominated by one particular species, whereas high values represent communities with many more species and a more equitable distribution of individuals between those species. We then did what are called random forest analyses, and these allow us to understand how various factors, in this case oxygen, temperature, and PCO2, affect diversity in the modern ocean. Don't worry about what these values represent, but basically a higher value represents a better explanation of the control on diversity in the modern ocean. So this suggests that oxygen is the strongest control of diversity in the modern ocean. What's shown here is a partial dependence plot. And so higher values here indicate higher diversity. And you can see that diversity basically drops off a cliff below about 0.5 milliliters per liter oxygen, which is about 8% of modern surface ocean levels. So we'll now go to a brief introduction about the late Permian world, because this is probably an unfamiliar world to most people. During this time period, all the continents were together in one supercontinent. You guys may have heard of this, Pangaea. And there was one big ocean, Panthalassa, as well as this kind of smaller, more restricted ocean, the Tethys. The ocean community at this time contained a number of fairly sessile, slow-moving, highly calcified organisms, many of which persist to these days, or to today, but nowhere near the abundance that they existed in the Permian. So these are things like crinoids, brachiopods, and the shelled ammonoids and nautiloids. On land, the fauna was dominated by synapsids, or the mammal-like reptiles like this Dimetrodon. And although these look like dinosaurs, they're actually more closely related to mammals. And at the end of the Permian, these entire ecosystems fell apart, disappeared. The Permian-Triassic mass extinction is the most catastrophic extinction in the history of the Earth. So what's shown here is the genus-level diversity in the oceans through time, from the modern back through the Cambrian at about 540 million years ago. And this is the number of fossil genera that we find in the fossil record. And you can see here that by proportion, the Permian-Triassic extinction was the biggest drop in diversity in the last 540 million years. So this is the late Cretaceous extinction. It's the one where the dinosaurs went extinct. And you can see that a roughly similar level of genera went extinct, but proportionally it was far less. So in the Permian-Triassic mass extinction, up to 80% of the genera went extinct. Now, we don't really have a good way to track how many species are in the ocean for various reasons, but if you do kind of back-of-the-envelope calculations on how many species are usually present in a genus, it suggests that up to 96% of species, basically all life in the oceans, went extinct at this mass extinction. And the latest date suggests that this happened really fast, at least in geological time, in less than 200,000 years. And it happened at the same time in both the marine and terrestrial realms. So there's been a lot of debate about the causes of the Permian-Triassic extinction. It's kind of the classic geological whodunit. But in recent years, geologists have tended to focus on what's called the Siberian flood basalts. What this is basically a vast outpouring of lava up in Siberia, northern Siberia. It's the biggest volcanic eruption on Earth in the last 500 million years. And its current extent covers about 2 million square kilometers, which is about the size of Western Europe, which also gives you some sort of a hint about how big Siberia is. Kind of the idea that most geologists have played with or believe for how this event happened was that there's volcanic activity that released an extraordinary amount of CO2, and this is both from the volcanoes themselves and from interaction with the rocks through the lava that the lava was erupting through. This CO2 led to global warming, like in the modern ocean, but this wasn't the only thing. This CO2 release resulted in a number of different kill mechanisms, at least 3, that we can see in the fossil record. So this global warming increased what we call ocean stratification. This is those density surfaces in the ocean that make it harder for oxygen to mix in. And this resulted in anoxia, or low oxygen zones, throughout the world's ocean. It also, the CO2 directly equilibrated with the ocean, causing ocean acidification, or a drop in pH in the ocean waters, as well as what's known as hypercapnic stress, which is basically the ability of organisms to deal with the CO2 and regulate their acid-base balance. But this wasn't the only thing. The CO2 release also interacted with this warm climate to cause intense weathering of all these new lavas that have erupted. Now, it turns out lavas are really rich in nutrients like phosphorus, that key nutrient for phytoplankton growth. So what happened then is you have this increased pulse of phosphorus into the oceans that led to eutrophication, and again to anoxia and hypoxia. So now I'm basically just going to go through a few of a little bit of the evidence for this mass extinction event, and evidence for the anoxia and global warming. This is a stratigraphic column, or basically a description of the sediments meter by meter, through a Permian-Triassic extinction section in Spitsbergen. And what you see here is that the latest Permian sediments are these nice, well-oxygenated burrowed sediments. And in the latest Permian, they're sharply overlain by these sediments here, these perfectly laminated rocks with absolutely no disruption, as well as other evidence for anoxia, well, geochemical evidence. Where we do find fossils in here, though, these are these chloria beds. It's only one single bivalve that can tolerate these conditions. And so it's this monospecific assemblage in this highly stressed environment. As I said, though, it wasn't just anoxia that did in the late Permian organisms. This is a temperature map, or a modeled temperature map, of the late Permian world. And these white areas are land. And what you can see here is that it's a relatively hot world, at least compared to modern. This graph over here is showing the change in sea surface temperature with respect to the modern ocean. So anything that's positive will be warmer than the modern ocean. So much of the oceans is in fact warmer. So this is already a hot world. The thing is then, there's evidence in the geochemical record for a further 6 to 10 degrees of global warming. And so people have suggested that the tropics here got up to 38 to 40 degrees Celsius, which is well over 100 degrees Fahrenheit. That's incredibly hot. There's basically very little to no animal life that can live in those conditions. And that's what we see in the fossil record. So this is a reconstructed map of the earliest Triassic world, after those anoxic events and those kind of greenhouse, hothouse events. And what people have suggested, there's basically a dead zone throughout the entirety of the tropics where there's no tetrapods present, no four-legged organisms present on land, and basically very little life in the oceans in the tropics, and especially none of the bigger life, things like marine reptiles or fish and sharks. And these are only existing in kind of these high-latitude refugia. So with this in mind, what caused the late Permian extinction, we can now move to conclude our talk with the future of the modern oceans. So when we think about the killer for the Permian-Triassic extinction, we think a bit of the flood basalts, but it's really not just the flood basalts. The real thing that caused all these problems is the CO2 release. And so instead, we can think of this as being driven by a CO2-driven perturbation to the Earth system. And it is indeed an Earth system. It's not just one cause and effect that did these organisms in. It's a cause and then multiple effects and knock-on effects that created this deadly trio of global warming, ocean acidification, and anoxia. And so once we're thinking about this as being caused by a CO2-driven perturbation, it's not that hard to replace the picture of the volcanoes with human-induced CO2. And note, the atmospheric CO2 is now 400 ppm and growing rapidly, and the rate of change is unprecedented in the last 25 million years. And there are some distinct differences with respect to the Permian. For instance, this whole weathering feedback wasn't operating. But we have other really important things going on in the modern, such as the nutrients from runoff and increased upwelling that are again causing eutrophication and further anoxia and hypoxia. So I'm a paleontologist. I'm not really an expert in modern global change, but I'm just going to briefly go through some of this evidence for how oceans and environments are changing in the modern ocean. Now, in putting together this talk, I was looking for a good slide on global warming, and I figured you guys had seen plenty of slides of increasing temperature through time. So I thought instead I would just tell one little anecdote related to my research that's kind of illustrated by this cartoon of these two polar bears trying to adapt to a warming world where there's no sea ice, and they're trying to fit in with this camo shirt. And this anecdote is that the Arctic is one of the places on the world that is experiencing the fastest warming. And as it's warming, actually, the grizzly bears are moving farther north. And as this is happening, the grizzlies are actually interbreeding and creating hybrids with the polar bears. And this is colloquially called the pizzly bear. And it kind of looks like a smaller, dirty polar bear with this funny little head on it. And this is just one example of all the different changes we're starting to see as the world warms. And it's particularly relevant to me because the last thing I need when I'm doing northern fieldwork is a new type of bear that's trying to get into my camp. So global warming is familiar to most people, but the other two causes of major global change might be a little less familiar. And the first is ocean acidification. And this is relatively easy to understand and to model. And it's basically as we're increasing CO2 in the atmosphere, that CO2 is equilibrating with the ocean and making the oceans more acidic. So this is the record from the Mauna Loa Observatory of atmospheric CO2. As you can see, it's going up in time, and as it goes up in time, the record of ocean CO2 from the nearby Station Aloha Observatory in the ocean is also going up in lockstep, and the pH is reducing. And this has real big implications for any organisms that make a calcium carbonate skeleton. If things get bad enough and the pH gets low enough, their skeletons will literally start to dissolve. The final global change stressor might be a little harder to understand the different causes because, as we talked about in those first slides, there's so many levers we can pull to change the oxygen levels in the ocean. So for instance, the deoxygenation in the modern ocean could be due to ocean warming because oxygen is less soluble in warm water. It could be due in some places to increased stratification because we're getting less mixing of oxygen into the oceans. Or in other places, it could be due to increased upwelling intensity. We're bringing more nutrients to the surface, fueling that phytoplankton growth and more decomposition. Whatever the causes in different places, we know from many data sets around the world that ocean deoxygenation is happening. And this is just a famous map, at least in scientific circles, of the shoaling of the hypoxic boundary. This is the 60 micromole per kilogram oxygen level off the Southern California slope. And you can see in many places that this oxygen level has risen 50 to 100 meters. The issue here is that these combined causes of warming, acidification, and deoxygenation decrease the habitat available for any particular species. So for most organisms now in the modern ocean, they're living in some habitat regime between waters, say this is for organisms on the continental slope and shelf, between waters that are too warm on the surface and have too little oxygen below. As we increase the warming of the surface ocean and increase the extent of the low oxygen levels below, we're going to squeeze the habitat for these different species. And for some species, those habitats are simply going to disappear. So thinking back about what we've seen in the geological record and throughout this talk, we could suggest that many areas of the world are going to have lower diversity. Perhaps in worst cases, down to these single monospecific assemblages like we saw in the aftermath of the Permian Triassic. We also might predict that there will be fewer predators based on the Polychaetes studies that I showed you, or at the very least, very big changes to the food webs and the interconnections of marine organisms. Finally, from a more practical level, we'll see big changes to fisheries, and this will particularly impact benthic fisheries, places where the oxygen spreads. It'll simply wipe out the habitat, or where the low oxygen spreads. It'll simply wipe out the habitat for those benthic fisheries. And also for organisms like billfish and tuna that have really high oxygen requirements. It's going to aggregate them along really small habitat margins, and it's going to make them really easy to fish and, unfortunately, to overfishing. Finally, these changes will cause big changes to biogeochemical cycles. The redox landscape, or the oxygen landscape of the modern ocean, strongly controls the biogeochemical cycles of different things like where carbon is buried, or the nitrogen cycle, which ultimately influences nutrients and food, etc. And so the point is that these changes are related to that Earth system. As we see changes, CO2-driven changes, it's not just oxygen, temperature, and PCO2 that will be changing, but the entire Earth system. So if we sum this up, we can see that the Permian Triassic mass extinction was driven by a CO2-driven perturbation to the Earth system. And that it is this Earth system. That's the important thing. And that as we change and increase CO2 in the modern ocean, we're seeing those exact same stressors of global warming, ocean acidification, anoxia, and hypoxia. And there are a lot of differences between the modern ocean and the Permian Triassic, especially with respect to the time scale of CO2 release. But this provides kind of an analog and a worst-case scenario for what might happen as we continue to increase CO2 levels. So I conclude simply with a quote from a recent review article on the Permian Triassic extinction. The in-Permian rock record cannot currently provide the temporal and spatial resolutions to make specific predictions about expected changes in the coming decades or centuries, but increasing evidence that the in-Permian mass extinction was precipitated by a rapid release of CO2 into Earth's atmosphere is a valuable reminder that the best and most sobering analogs for our near future may lie deeper in the Earth's past. Thank you.